Welcome everybody. We have the pleasure of having today Giancarlo Fortino from the University of Calabria. Giancarlo Fortino is full professor at the Computer Engineering at the Department of Informatics, Modeling, Electronics and Systems of the University of Calabria in Italy. And his research interests include wearable computing systems, e-health, the Internet of Things, agent-based computing, and more recently, generative AI in education. So today, he's going to talk us about a very popular topic nowadays, no? Generative digital twins, with this title of a novel approach in the IoT edge cloud continuum. Professor Fortino, thanks for joining us, and you can go ahead and present your talk. Thank you.
Okay, thank you very much for your introduction. First of all, I'm very glad, to be in this context in order to deliver my talk related to, as Rosa said, related to generative digital twins. That is a pretty hot topic, not only from our personal research perspectives, but at the international level, generative AI-based digital twins are becoming known and also are becoming a mainstream technology. So today, again, the title of my presentation is the one announced. And first of all, I'd like to give you just some quick look at my laboratory that is named SPEME. SPEME is an acronym. It stands for Smart Pervasive Mobile Systems Engineering, even though SPEME is an Italian word that means hope. Okay. Currently, we are a pretty large group, more than 40 members. I'm pretty honored, to coordinate such a high number of people, including associate professor, assistant professor, postdocs, and notably 18 PhD students coming from many different countries in the world, like Italy, India, Colombia, Pakistan, China, Bangladesh, Romania. We are involved in multiple projects, international projects, national projects, but also industry-oriented projects. So just to give you, to let you know my collaborators, so you can look to diversified faces from all around the world. Okay, so this is the outline of my presentation. First of all, I'd like to shed a bit of light on the concept of edge intelligence. So we worked a lot on this concept, and as we will see in a little while, we are mainly based on a systematic meta-survey in order to better understanding the very notion of edge intelligence, specifically in the context of Internet of Things. Then I will try also to give you an overview of our European Research Innovation Action project named MLSISOPS, but I will be very brief, just to give you some information and some links, to the project. Then my main talk will be on the transition from conventional or traditional digital twins to generative digital twins. So we will see this transition over a couple of decades. Okay, and then I'd like to receive some questions, and then we can interact a little bit. Okay, first of all, I'd like to introduce my own vision on Internet of Things and my own definition of Internet of Things that a little bit deviates from the mainstream definition of Internet of Things that is mainly based on a telecommunication perspective, like a planetary network of interconnected objects based on standard communication protocols. In my opinion, Internet of Things is much more. It's a system of systems, and the basic building blocks of this kind of planetary platform are smart objects. So smart objects indeed got different characteristics and features like the capabilities of sensing, actuating, networking, processing, storing, but specifically they are able to proactively develop and to proactively execute tasks. So this is let me say a vision that is oriented to multi-agent systems. So this is, of course, based on my previous experience, extensive experience on multi-agent systems. And, in our opinion, Internet of Things, again, will be a planetary network of agents, okay, that we call smart objects. What's the status of the Internet of Things right now? We moved from the first generation to the current one. The first generation was established many years ago, at least 20 years ago, more than 20 years ago. I can remind you that the term Internet of Things was coined by Ashton in 1999, so more than 20 years ago. In the first generation, Internet of Things was mainly based on sensor networks or wireless sensor networks. Then such kind of networks were integrated into ICT systems like ERP, supply chain, and so on and so forth. Currently, the current generation is, of course, mainly driven by AI with this new concept of edge intelligence that I will introduce in a little while. So AI is strongly embedded in the IoT, driving mainly, all the activities that will be performed at the edge, okay? And another important aspect that is maybe more important from the industry viewpoint, but also from, the university academy viewpoint, is that the enterprise IoT market is increasing. Okay, is still increasing, about 20%. So this is something that we have to consider also in order to develop innovative use cases, innovative application in this domain. I give you some numbers because these are emblematic in order to understand better, the importance of this domain. We already have billions of deployed devices, almost 150 billions of already deployed devices, including different areas like smart homes, utilities, car, factories, and so on and so forth. The market is $1 trillion market that was pretty resilient even to the pandemics. And also there are substantial investment in enabling technology for the Internet of Things that are 5G, Wi-Fi 6, augmented reality, and so on and so forth. What's the final goal? In our opinion, the final goal is to create this Internet of Things ecosystem where humans and machines, so we have to consider that humans are and should be always in the loop of such kind of platforms. Each of them equipped with autonomic and cognitive skills are able to provide new services. So the real drivers of the Internet of Things are not the objects themselves, but they are the services the objects are able to provide, or the systems made up of multiple objects are able to provide. Okay, now let's start to move on the concept of edge intelligence that is, in my opinion, fundamental in order to create a smart Internet of Things. And as I already stated, we already have more than 150 billions of connected devices to the internet. They are able to generate almost 100 zettabytes of data at the network edge. So, it's unfeasible to try to bring such data onto the cloud. We need to be able to process such data as soon as the data are produced. And this is the very concept of edge computing. And then you can see, the typical conventional architecture of edge computing, in which you have the device layer at the bottom, then you have the edge layer in the middle, and then also the cloud layer on top of the architecture. What are the benefits? The benefits are clear: faster response times, improved reliability, and enhanced data security. Of course, we have to pay something, because if we adopt an edge computing architecture, everything will be distributed, okay, not centralized anymore, as you know, when you use a cloud. And then, of course, you have to manage, you have to deal with challenges like many distributed devices, okay, and also we have to ensure data consistency across the network, and this is something that it is not always possible, okay. Okay, so again, our objective is to inject, embed intelligence at the edge of the network. And we have to say that even before, you know, the emergence of generative AI, you know, 2022, with, you know, the peak of the iceberg that was ChatGPT, anyway, we already were able to create a huge body of knowledge of in the AI realm, specifically methods, methodologies, algorithms, tools, able to plan learning and reasoning. Okay, this is not new. This is something that we developed over the past 40, 30 years. Okay, and it's important to say that the integration, and now we will see in which way this integration was created, the integration between AI and edge computing led to this concept of edge intelligence, and again including main features coming from the two different worlds, from AI and from edge computing. So with multiple benefits, the same ones, you know, I mentioned 1 minute ago, related to edge computing, like, you know, reduced costs, latency, and data traffic, or enhanced security and privacy. But if we are able to mix AI with edge computing, we could improve even the decision making at the edge. So we don't need to wait, you know, to go onto the cloud in order to have even complex decision making. Everything sometimes could be performed at the very edge. In this way, we are able to minimize costs, and then to deliver decision in a faster way. Okay, in order to understand better this concept of edge intelligence, we developed a survey a couple of years ago. The survey was published in 2023, so 2 years ago. I strongly recommend you, you know, to download the paper. The paper is in open access, and in this survey we were able, you know, to provide an outlook of the current literature related to edge intelligence. Let me be short on this, because anyway you have, you know, the link to the paper, and then again you can download it and read it in detail. At the end of the day, the survey, that is a systematic one, is based on the Prisma methodology. We were able, you know, to create this framework in which, you know, the concept of edge intelligence is central to the framework. And then we have different dimensions, like which kind of definition about edge intelligence is a revolutionary or an evolutionary definition, which kind of techniques are already there supporting the concept of edge intelligence, and then we can have something that maybe some of you already know, like, you know, having edge training techniques or edge inference techniques based on algorithms that are able to catch information, to catch code, in order to send code, you know, from the device to the cloud and back. So we already have multiple methods based on the concept of edge intelligence. Another important aspect is which kind of architecture we could exploit in our deployments. And there are already several edge cloud or edge for cloud architecture that could be reused in order to create this distributed platform based on the edge intelligence concept and multiple topics, edge training, edge inference, edge offloading, even the possibility to create models at the very edge, using even processors at the edge devices, and so on and so forth. So we already have a pretty interesting body of knowledge that we could reuse in order to, again, to apply the concept of edge intelligence. Okay, let me just discuss a little bit about the lesson learned about, this study we performed, that indeed it was not just a study, because we are also, developing architecture techniques and algorithms in the context of edge intelligence. So first of all, my first statement is that IoT systems, in order to unleash their full potential, need to incorporate effective intelligence at the edge. Edge intelligence is not anymore a promising field, is already a well-established field that could be exploited again in order to boost the development of intelligent IoT systems. Another important aspect is how to move from the university work to the industry. And this is something that is associated with standards or standardizations efforts like, HiPEAC, that is a standard related to mobile edge computing. And, this concept of edge intelligence could be embedded in such kind of already deployed specifications, deployed in IoT gateways. But if you'd like to have more intelligence, of course, we need to integrate edge intelligence concepts inside this standardized infrastructure. Another important aspect is how to deal with the edge cloud continuum, how to, again, inject edge intelligence inside the edge cloud continuum in order, again, to manage the infrastructure using the continuum concept. In order to clarify better, what I said, I'd like to exemplify the edge cloud continuum using our project that we developed in the last 3 years. So the project will end at the end of this year. The name is MLSysOps. And MLSysOps is based on this concept of the device edge cloud continuum, where you have to treat, you have to deal with your system not just as a specific layered system, but from the most external layer, that is in our case the IoT layer, till the most internal one, that is the cloud. You need to treat these slices in a continuum way. So your system automatically should be able to perform operation independently from the layers in which this operation is being or will be carried out. And of course, there are already a bunch of papers on this concept. One of the reference is the one I put at the bottom of this slide, 2021, almost 5 years ago. But there are many others. This is another one that was developed even earlier, 2018. And such kind of infrastructure were mainly based on ad hoc solutions, ad hoc methods. What we are looking for is to create a systematic way to manage the concept of continuum, and this was the main objective of a call that was launched 3 years ago related to project EU-funded project in the area of edge cloud continuum. In our case, our project was approved out of other five, six projects, and the goal of our project was, as you may read from the title, to create an infrastructural environment in which machine learning was able to drive the realization of the concept of edge cloud continuum. If you'd like to have more information, I will give you now some information about our project, but if you'd like to have more information about the project, please connect to the website that is mlcsop.eu, or please, contact me in order to have even additional discussions or information. You see that, we are several partners from university, research centers, large medium, medium small, large enterprises, and the coordinator is University of Tessel in Greece, while the deputy coordinator is from University of Calabria. Okay, so what's the goal? The goal is not to optimize applications, is not to design applications, but it is to create a new device edge cloud infrastructure that is able to, at runtime, to optimize existing applications that are running atop the infrastructure by optimizing in real time the infrastructure itself. So this was the main goal, and as you may see, there is a management plane that is atop, the architecture, the typical architecture based on the far and the smart edge, the edge infrastructure, and the cloud, a management plane that should be able to optimize the management of the computing, the storage, and the networking resources. And the approach we adopted is an approach that was introduced many years ago in the context of multi-agent systems. That was the MAPE approach introduced by IBM. MAPE stands for monitoring, analyzing, planning, and executing. So this loop was reused so that we are able to monitor the infrastructure. We are able to analyze, the data coming from the infrastructure using mainly two machine learning methods, one that should be explainable and the other one that is based on the concept of continual learning. And the decision making is performed so that the execution of the actions we are going to take will try to enhance the efficiency of the infrastructure and implicitly enhancing the application performances. The realization of this idea was mainly based on super peer multi-agent systems. So you can see the phases of multiple color. Such phases represent agents in a multi-agent systems, and we have agents at the different levels of our infrastructure, at the node level, and the infrastructure slice level, and at the continuum level. So the interaction between the agents constitute again a super peer infrastructure that is able to optimize in real time the infrastructure over time. These our results were also reused to support several use cases. You can see that we applied this concept in four main use cases: smart agriculture and smart city, that were developed by small medium enterprises, and smart wearable system and smart drone system that were developed at the premises of our department at the University of Calabria and at the Realil in France. Okay, now I'd like to focus the attention in my last 15, almost 20 minutes on this transition from digital twins, conventional digital twins, to what we named as generative digital twins. What's a digital twin? This is a conventional definition that was given by Hughes in 2018. A digital twin is an executable virtual model of a physical thing or system. Okay, so this is a well-established definition. What are the key components? The key components were provided by Greaves in a white paper of more than 10 years ago. You know that digital twins were born mainly in the context of manufacturing, smart manufacturing. So the key components are a physical object, so you need to have an object that you can touch, okay, like you can see here in the picture. Then you have a virtualization of this object, so you got the logical object that is the digital counterpart of the physical one. And then you got also the virtual space and the connection between, the real space and the virtual space. In the original model, you didn't have any feedback, but, in the variants of the original model, you could also have feedback coming from the virtual to the real space. Okay, evolutions of this model were mainly driven by artificial intelligence, even edge intelligence. Okay, recently, 2023, we introduced a variant, an evolution, let's say, of the basic digital twin model named opportunistic digital twin. Okay, the concept of opportunistic digital twin is based on edge intelligence. So, according to our definition, an opportunistic digital twin is a edge intelligence powered digital twin able to opportunistically adapt to and act upon the physical environment that surrounds them. So this definition is very close to the multi-agent systems definition. Okay, so digital twins become a sort of agent or in a multi-agent system. Okay, and of course, AI, edge intelligence, is able to boost digital twins beyond, the original digital mirroring model in order to support adaptive learning, in order to support pattern detection, in order to support predictive maintenance. Okay, so edge intelligence was, the basis in order, to allow this, let's say, evolution. I'd like just to give you an example of opportunistic digital twin. Along with our colleagues from Telecom Sud Paris in France, specifically my colleague Noël Crespian and Minerva, we created this AI-based traffic monitoring system. The vision is, the classical vision in order to optimize traffic in smart cities by using smart IoT-based technologies. So the key features of this system is to exploit edge intelligence technology in order to process information as soon as this information is captured at the edge. Another important concept is to have synthetic sensing over general purpose devices, and specifically an approach that is not a top-down approach, but it's a classical machine learning driven approach, and then a bottom-up. So we are based on the data in order to create the models. So mainly we were focused on intersections, and in such intersection, as you can see here in the picture, we were able to capture images of the vehicles. Okay, our objective was to detect the vehicles in real time, and then we created, this kind of device edge cloud continuum infrastructure system. Okay, where at the device you have heterogeneous devices like tiny devices like Arduino Portenta devices, but also much more powerful devices like, for example, a Google Coral Dev board, where you also have GPUs, and then you can embed the vehicle detection algorithm that is mainly based on computer vision. So you need more computational power with respect to a simple Arduino Portenta board. Then, of course, at the middleware level, we have a framework based on MQTT and Node-RED, and at the cloud level, of course, we have databases able to archive data coming from the different layers of the system. So just to tell you that the system was a pretty heterogeneous one, both from the hardware viewpoint and the software tools viewpoint. It's important to note that when you deal with such kind of edge intelligence systems, you need to trade off between several parameters. In our case, the main parameters are two. From one side is the speed, so the latency, coming from the execution of the models in order to detect the vehicles, okay? And from the other side, the accuracy. So we need to be fast, but we need also to be accurate enough to be able to detect the vehicles, okay? So this is a trade-off. Of course, we don't have formulas. In this case, we have to acquire experimental data in order to provide useful insights. And from the latency viewpoint, you can see here that if you use simple pre-trained models, like, for example, SSD MobileNet, the latency is very small, but if you take a look at the accuracy, even the accuracy is not so good, okay? But if you use, heavier models like the MTD or the T1 model, of course, the accuracy will increase. And again, you have to find a compromise, a trade-off, in order to select, the right model for your specific purposes. Another important aspect is what we said at the very beginning. So we cannot move data onto the cloud because you have a lot of data, but you have to process them as soon as you are able to collect them. And this is another experiment highlighting, this best practice, okay? So we have a fully edge-based system and a fully cloud-based system. And then in the fully edge-based system, we collect data and soon process data. In the cloud-centric solution, we send, the video stream onto the cloud in order to be processed. How much can we save? A lot. I will not go in so many details, but if you consider one-day interaction between edge devices and the server, you have to transmit 3.34 terabyte, okay? If you use the cloud-centric solution. If you don't use the cloud-centric solution, you have to transmit just 0.8 gigabyte. It means that the fully edge-based approach allows to save 4 order of magnitude of bandwidth less. Okay, so this is something that, is a, let's say, experimental witness that it's important to move computation rather than data. Okay, let's go back to the digital twins from the methodological viewpoint. This is you can see in the picture the evolution of digital twins from 2000 to now. The last let's say 20 years. First of all, we had this mirroring world, then the very concept of digital twin was introduced. Many different variants of digital twins, mainly based on different AI methods, cognitive DT, opportunistic DT, and other kinds of DT. Now, we are in in the era of using generative AI to support digital twins. So this is why, you know, recently we published a paper in the IEEE IoT magazine that was, you know, got the same title as my talk, you know, generative digital twin towards next generation of IoT based edge cloud infrastructure. But let's try to understand better what are the characteristics of generative digital twins. Let me read, you know, the definition we provided, and generative digital twin is a novel approach which seamlessly merges classical digital twin model-driven system with generative AI, creating a dynamically shaped system with exceptional adaptability. So this is something that is mainly provided by the characteristics of different genAI methods, not only, you know, LLMs, not only LLMs. We will see which kind of methods are able to support the generative digital twin concept. So in this table, you can see the most important properties from our perspective that are not supported or well supported by traditional digital twin, but they will be better supported by generative digital twins. Okay, so the properties are adaptability or real-time modeling, data quality, data generation and augmentation, interaction with physical asset, but also with human operators, and simulation. Okay, classical digital twin are able to address these properties in a static way, mainly in a static way. Generative digital twins got a new potential, you know, a new potential to make everything more dynamic. For example, if you consider that data, when you collect data, you cannot assume that the data collected are perfect. Most of the time they are not. You know, they are faulty, you got missed samples, they are dirty, and so on and so forth. So you need effective methods that on the fly are able, you know, to restore them or to amend them, and so on and so forth. So generative techniques could be able to support this concept. And another important aspect is, of course, the interaction with IoT devices that could be based on natural language and not on static protocols. And simulation, you know, that is mainly based on statistical distributions, but sometimes, you know, we are not able to capture real-world data using statistical distribution, then we have to exploit generative techniques in order to create real or more realistic patterns. What's the state of the art? The state of the art is, let's say, embryonal, is emergent, and mainly based on three techniques and the related variants of such three techniques. And these techniques are variational autoencoders, GANs, and transformers. The first one is very good for learning complex data distribution, detecting anomalies. The second one, GANs, are very good to try to replicate intricate patterns mainly related to cyber-physical systems. And of course, transformers are very good in order to generate not just text, images, video, but you can use them also in order to generate IoT data. Okay, this is something that maybe is a bit newer than the use of text, images, and video. But of course, first of all, we need a new reference architecture for generative digital twin. So we are working in this direction to define a reference architecture for generative digital twin. And this is, let's say, a kind of instantiation of quasi-standard digital twin architecture based on perception, data processing, representation, and decision and control layer. Okay. And another important aspect is to provide a methodology. because if you have a problem, you don't need just an architecture, but you need a methodology that goes from, the requirements analysis till the deployment of your solution. Okay, and this is another important aspect that is not yet, well studied, well developed, and in this case, based on our experience on definition of different methodologies, methodologies for agents, methodologies for Internet of Things. Now we are defining a new methodology, even based on some standardized digital twin architecture, as you may read over there. IEEE, VNB, ISO are trying, to propose a new digital twin and standardized digital twin architecture, and this should be key in order to develop again generative digital twins systems. Okay. Okay, just 5 minutes and then I will conclude. I'd like just to show you let's say a basic use case that could give you some information more on what is a generative digital twin. And again, we reuse the same context as the previous use case, that is a smart city, and specifically intelligent transportation systems. This is a use case we developed recently. Indeed, the publication refers to end of last year in the IEEE World Forum on IoT. And again, the context is the same. I introduced in the first use case, but in this case, the objective was different. The objective was, given an intersection, you can see here an intersection, and specifically refers to a pretty famous intersection in Tokyo, in Japan. The idea is to predict the trajectories of the vehicles in this intersection. Okay, in this case we reused generative AI methods, and we delivered this infrastructure. This is our infrastructure in which, using YOLO version 8, we are able to grab the vehicles in the intersection over time. Then if such frames are corrupted, then we are able to restore them using a Roberta approach, that is a kind of transformer that is able to restore data. And then, based on an LSTM infrastructure, we are able to predict the trajectories using 5 instant in time in future. Okay, so this is a non-real-time application. Okay, so this is performed, of course, offline, but it's a kind of proof of concept of the potential that a generative digital twin approach could provide. And if we take a look at the results, specifically here, you can see the accuracy of the method based on non-corrupted data. The prediction at 1 instant in time ahead, at 2 instant in time ahead, and so on and so forth, till 5 instants in time. Okay, of course, the prediction at 1 instant in time ahead is the most accurate ones. You can see more than 85%. Of course, if you try to predict the future, this prediction accuracy will go down. Okay, till less than 70%. You can see 2 different LSTM methods that are, the common ones: ground recursive and ground teacher forcing. And then the ground recursive is a bit more, a bit higher performance than the other one. But it's important to note that if you don't have, clean data, but you have corrupted data, for example, 25% or 35% or 45% of corrupted video frames. In this case, you can see here from the plot, the accuracy will fall down till less than 60%. Sorry, less than 40%. If we exploit, so you have to see the orange bar. If we exploit the reconstruction based on Roberta, then we can improve a lot, the accuracy, because we can reconstruct the original data. Okay, so this is just to show you that the exploitation of such kind of methods could impact positively the accuracy of the overall system. Ok, allora let's try to summarize and also comment the main results coming from this research. The first point is what we try to advertise, that is IoT Edge Cloud Continuum is become a best practice. So this is something that is not is not becoming so at the university level, but specifically in industry environments. Okay, another important aspect is that it's important to push intelligence, machine learning, generative AI at the IoT edge. Okay, this is becoming a must, is already a must. Of course, I don't want to say that you can get rid of cloud. Absolutely, you have to consider, the device edge cloud continuum. Okay, not, but injecting intelligence starting from the very edge is fundamental. Another important aspect is that it's important to exploit the concept of digital twins, but specifically the new ones based on AI and on generative AI, because this could become important to effectively and efficiently develop again the concept of device edge cloud continuum. And the last point is a kind of disclaimer. In this talk, I didn't address at all, trust, security, privacy issues. This was another talk of mine that I'm used to give in the past. But anyway, I'm pretty open to have questions on the last point. Yeah, publication possibilities. I'm the editor-in-chief of these two series: Internet of Things, published by Springer, and Human Machine Systems book series, published by Wiley. So please, if you are interested in develop edited or authored book project, contact me. Yes, and another slide is, I'm ambassador of AI Scholar. But anyway, please contact me if you'd like to, again, if you think, to be able to submit a proposal for such kind of book series. And thank you very much for your attention.
Thank you very much, Giancarlo, for this very comprehensive talk. It's been great, very complete. So for the audience, you can write questions on the Q&A channel anytime, but in the meanwhile, I will start asking some questions. So I saw in slide 20, you were presenting, well, we're talking about continual learning, no?
Yeah.
So the continual learning, how do you implement it? Is really that you are doing this process all the time, or is that after you are on operation and at the given moment you decide to start the operation, the continual learning? And if it's so, what makes you decide, no, that you need to do?
Yeah, the continual learning is embedded in the MAPE loop. The MAPE loop is the monitoring, analyzing, planning, and execution. So the continual learning is not only at the monitoring step, okay? It is always on. It is always on in order to drive, again, not only some decision making, but also the way in which the collection is performed. Okay, so the algorithm takes these two important input. One is coming from all the resources of the infrastructure. The other one is related to the decision making. It means the decision taken so far, and it merges the two aspects. Okay, the decisions and the current status, let's say, formed by, again, the data coming from the infrastructure. But it's a continuous process, okay? It is performed continuously, okay? So it's time driven, it's not event driven, okay? It's time driven, and the time could be adjusted, okay? For example, for some application domain, it could be a given delta. For other ones, another one. This should be determined experimentally, okay? But in our case, is time driven, is not event driven. Even though I know there are other approaches that are event driven approaches.
See, that's why I was asking. We have Fernando. I see now a question from Fernando, which is doing the thesis in a related topic, okay? And that's why we were asking, because we are considering how to implement this continual learning. So I'll read you his first question from Fernando. So regarding the communication digital twin to digital twin using generative AI, how can that work correctly? I mean, several unexpected scenarios could arise, but that can be answered by the DT. But wouldn't it be more simple to create some set of rules for communication and use them?
Thanks a lot for the question, because this relates to one of the properties we indicated as important properties. So interaction between digital twins and systems, or between among digital twins. Okay, so this is something that indeed we have not explored yet. Okay, so we were much more focused on data, okay, on the generation of data, or on the reproduction of patterns of data. But of course, here we need to understand the trade-off between a fully, let's say, LLM-based approach, and a hybrid one in which you could have already existing protocols, okay, there, already existing protocols there, and LLMs that are able indeed to allow for a more, let's say, non-deterministic interaction. So this is something that we are exploring in another use case, okay, but not in the one I showed today.
Very good. I will read first the question by Tulio. So if we have time, then we will ask the final one from Fernando as well. So Tulio Bardana is asking, at some point of your talk, you observed that there are cases when moving code is preferable to moving data. I happen to agree with that very much. My question is whether you are finding widespread consensus or rejection to this notion. I agree, by the way. Also.
Yeah. Yeah, sometimes you need to, let's say, process the data as soon as. For sure, in the context of IoT, this is the case. maybe 95% of the times. In other contexts that are not based on IoT, maybe you need to send your data onto the cloud. But again, if you refer to the IoT context, this is a truth, let's say, most of the times. Okay.
And then I'll take a question from
Yeah.
Zia or Rema in the chat.
Yeah, there
Is
is
it
one.
possible to deploying these twins to wearable system? And using these systems is to make these devices more intelligent or smarter, because this system generate large amount of data. What's your suggestion?
Yeah,
using this type of
definitely. I mean, we developed wearable systems since 15 years so far. We also virtualized them. We also got digital twins of wearable computing systems. Definitely. I mean, you could create your digital twin inside or even outside. It depends on the computational capabilities of your device, but definitely you can virtualize your wearables into one or more digital twins. It depends, of course, it depends on the application, okay? But definitely, yes. You can apply the concept of digital twins for whatever device, included, wearable devices.
Okay, so thank you very much, Giancarlo. It's been a great talk.
Thank you very much.
Thank you, the audience,
See you
also for attending the webinar. Thank you very much.
Bye-bye.
Bye-bye.